Today on Macaulay Math, we're doing vectors. Intro. Okay, good day. I'm Professor Macaulay. This is Math 150 Pre-Calculus, Lesson 31 on vectors. Our goals for today: we're going to represent vectors as directed line segments and write them as component vectors. We're going to perform basic vector operations such as addition and subtraction and scalar multiplication. We're going to write a vector as a combination of unit vectors, and we're going to find the direction angle of a vector. Vectors are a fundamental concept of mathematics with many applications. Vectors are used to represent quantities that have magnitude and direction and are used extensively in the study of physics. For example, vectors allow the calculation of how many forces of varying strength from different directions can affect a given body. They are also used in problems involving projectile motion. Let's get started.
Okay, let's start with the definition. The component form of a vector is the ordered pair for the endpoint of a vector with an initial point at the origin. So when you are given this bracket, this little arrow looking bracket, xy, they are saying that that is a vector that starts at the origin and ends at xy. So if I draw in a coordinate plane and I call this y and I call this x, and I give you the point xy is right here, then the component form of the vector that starts at the origin and ends at the point xy, that is what the component form of the vector is. The magnitude of the vector is just the length of the vector, or the distance from the origin to the endpoint, and that is denoted with the double bars. Also, vector is denoted with a little half arrow, and sometimes it's denoted with a bold. So, and you can't, it's very hard to see, and I understand that. But if you see something like this with that half arrow, that is a vector V. And if they just bold it, like they make it extra bold, that is also vector V. Okay, the magnitude is just the distance, and so that should be familiar to you, and because it's just the Pythagorean theorem again, so the square root of a squared plus b squared for a vector v that has a and b as its components. Scalar multiplication: if you are multiplying a number by a vector, you just multiply each of the components by that value. In scalar addition, if I add vector AB to vector CD, I am just adding the x components and the y components. There are some standard unit vectors. Vector I is the vector 1, 0, so the unit vector, just like the unit circle, is of length 1. It is 1 unit along the x-axis. And the j vector is similar. It is a 1 unit along the y-axis. To find the unit vector, and a unit vector has the same direction as the original vector, but it has a magnitude of 1. So the unit vector is equal to 1 divided by the magnitude of the initial vector times that initial vector. So this becomes a scalar times that vector. For vector addition and scalar multiplication, the following properties hold true. So the commutative property of vector addition holds true, so you can add your vectors in any order. You can associate your vectors in any way. The identity property of vector additions: if you add the 0, 0 vector to both, that is the identity property. The inverse property of vector addition. The associative property of scalar multiplication, the distributive property of vector and scalar multiplication, and the identity property of scalar multiplication. As an example, show that the two vectors are equivalent, and I'm giving you a little note here. Two vectors are equivalent if their magnitudes are the same. So what we will do is we will find the magnitude of each vector. So we'll start with this vector u. So the magnitude of vector u will be equal to the square root of, now these vectors are not in component form. We're going to have to find the x component and the y component to calculate the magnitude. So what we'll do is we'll take this n value, so we'll go -3 minus 0. That will, and then we'll square that, and then we'll add that to the -4 minus 4, and then we will square that. That will give me, let's see here, square root of -3 squared plus -8 squared, and -3 squared is 9, 8 squared is 64. That'll give me 73. And then do the same and find the magnitude of vector v. Again, we're just going to subtract, so I'll go 0 minus 3 plus -5 minus 3. And again, I get the square root of -3 squared plus -8 squared, which will also give me the square root of 73. And so since these two magnitudes are the same, and these two don't reduce because 73 is a prime number, so since the magnitudes are the same, the vectors are equivalent. All right, next example. It says find the component form of the vector that has an initial point of -2, 7 and a terminal point of +5, -17. So what we're really trying to do is to see what would happen if the vector was the same length and went in the same direction, but instead of starting at -2, 7, it started at the origin. So if I make a clone of this vector and I move it so that it's in this point, when I find this x, y right here, that will be my component form of the vector. So to do that, what we will do is we will subtract the start from the finish. So my component form, and I'm going to label this as a vector v. My vector v will be equal to, and I'll use that bracket symbol because it is going to be a component form, and we'll subtract the start from the finish. So if I'm subtracting from, the finish comes first. So I'll go 5 minus -2, comma, -17 minus 7, and again we'll use that second bracket. So I have as my final answer -7 minus a negative, that's like plus a positive, so 5 plus 2 is 7, and then -17 minus 7 will be -24. And that seems reasonable based on my diagram, so we will say vector v and put a box around all that and move on. Okay, next example. It says given the component form of vector u is 5, 3 and the component form of vector v is -4, 0, find vector u plus vector v, find vector u minus vector v, find 2 vector u minus 3 vector v, and then half vector u plus 4 vector v. So vector u plus vector v will be me just adding the corresponding coordinates. So if I go vector u is 5, 3 and vector v is -4, 0, I am just going to go 5 minus 4, comma, 3 plus 0. And really this is 5 plus -4 because it's -4 there, which will give me the component form of that vector will be 1, 3. And then if I subtract, I do a similar operation, except I have a subtraction here. And so in this one, I will have -5 minus -4, and then I will have 3 minus 0. Now 3 minus -4 is like a plus, so 5 plus 4 will give me 9, and then I still have 3 there. Alright, if I want to do 2u minus, if I want to do 2 vector u minus 3 vector v, I'm going to rewrite that as 2 as a scalar multiple times the 5, 3, and then I will subtract that from 3 times the vector v, which was negative 4, 0. And so scalar multiple says that I just multiply the number out front times each of the components. So 2 times 5 will be 10. 2 times 3 will be 6. And I'm subtracting still. So 3 times negative 4 will be negative 12. And then 3 times 0 will be 0. And so here I will have 10 minus negative 12, comma, 6 minus 0, which will give me as my final answer for this one, again, plus a positive, so I will have 22, comma, 6 as my final answer there for that one. And then finally, if I want to do this addition, I'll go a half times that 5, 3, and then I'll go plus 4 times that negative 4, 0, and we'll distribute the scalar. That'll give me 5 over 2, 3 over 2, plus negative 16, 0. And so if I want to add these, I'll have to go 5 over 2. Well, how many halves are in negative 16? There are negative 32 halves in 16, and then I have the 3 halves and then plus 0. We don't have to find a common denominator from that, and we'll say our final answer for this one, 5 and negative 32 is negative 27, and then 3 halves plus 0 is 3 halves, and that is our component form of that vector. All right, next example. It says find a vector with the given magnitude in the same direction as the given vector. So here I have, and let's just draw a diagram here real quick. I have a vector that goes back to negative 12 and down to negative 5. And so what they want me to do, they want me to draw in a vector here that is in this same direction, but has a magnitude of 3 units. And so what we'll do is we'll go back up here and I will find the unit vector of the given vector and then just multiply that by the scalar 3, and that will scale it up to a length of 3. So first thing that we will do is find the unit vector, and that is going to be, so I'll say unit vector that is 1 over the magnitude of u times the component form of u, which we already have. So that will be equal to 1 over. Now the magnitude of that is just the square root of negative 12 squared plus negative 5 squared. And then we multiply that by this 12 negative 5. And so if I do that calculation, 12 squared is 144 and 5 squared is 25. So the square root of 44 plus 25 is the square root of 169. And that'll give me 1 over 13, because the square root of 169 is 13. And when I distribute that, I will get negative 12 over 13, comma, negative 5 over 13. Now, if you plug this into the magnitude formula, you would get a distance of 1. And since we want it to be a magnitude of 3, all we're going to do is we're going to take this up and we're going to go 3 times this vector. So I got negative 12 over 13, comma, negative 5 over 13. And distribute that 3 again. So negative 12 times 3 will be negative 36 over 13. And then 3 times negative 5 will be negative 15 over 13. Unfortunately, 13 is not a factor of either 36 or 15. So that is our final answer. And again, if you found the magnitude of that, you would have a distance of 3 units. All right, next example says find the magnitude and direction angle of vector v. So we want to find the magnitude, so we got to find the length here. So we want to find that magnitude of the vector v, and then this direction angle will be we can either find that angle there and call it negative, or find all the way around there. Just to keep it simple, I'm going to find that smaller angle there. Here they give it to us in terms of these unit vectors. And so if I go back up to the definitions at the beginning, I is 1, 0 and j is 0, 1. Now I'm going to show you how to do the whole thing, but I'm also going to tell you the shortcut. And once I've shown you how to do the shortcut, you can do the shortcut that way for the rest of vectors. But what they're technically asking you to do is they're technically asking you to go to 8 times that unit vector 1, 0, and then minus 3 times that other unit vector 0, 1. And when I distribute, I get 8, 0, and then I would get, and then I'll distribute a negative, so I'll make this a plus in this case, 0, negative 3, and then when I add them, I would go 8 plus 0, comma, 0 minus 3, which would give me 8, negative 3. So we did a lot of work, and so essentially from this point, if you see it in this form, 8i minus 3j, you can go right down to 8, negative 3 and skip all this stuff. All right, so the magnitude of vector v will be the square root of these two values, so 8 squared plus negative 3 squared, and if I'm not mistaken, we've already done that a couple times. That ends up being the square root of 73. Yeah, we did that all the way back up on this first one, 8 squared and 3 squared, 73, so we don't have to do that work again. And then this angle measure theta, well, if I think about it, if this is 8 and this is negative 3, then I have a right triangle where this side is negative 3 and that side is 8. So the opposite side is negative 3. The adjacent side is 8. I can use the simple SOHCAHTOA and say that the tangent of theta is equal to the opposite negative 3 over the adjacent side 8. And then say theta is equal to the arctangent of negative 3 over 8, and since we've got theta there, let's go back to Desmos and check to make sure you are in degree mode, and then we'll just type it in, arctangent of negative 3 over 8. That gives me negative 20.556. degrees. I'll put a box around that, and we have found the magnitude and the direction angle of vector v. Now here they ask me to find the component form of vector v given its magnitude and angle that it makes with the positive x-axis. So this question is essentially asking us to do the opposite of what we did before. They want me to find this x value and this y value because that would be the components of this vector. So I am going to, in this case, use the fact that this magnitude here is a hypotenuse of a right triangle and get my x value by going the sine of 135 degrees is equal to the value for y, which is the opposite, over the hypotenuse, which is 5 halves. And then y would equal, I'll multiply both sides by 5 over 2. That'll cancel on this side. So I'll have 5 halves times the sine of 135. Similarly, I can say the cosine of 135 is equal to the adjacent side over the hypotenuse, so x over 5 halves. And then x will be equal to 5 halves times the cosine of 135. Now, the good news is that 135 is already on the unit circle. We know it. The sine of 135 is square root of 2 over 2. The cosine of 135 is negative square root of 2 over 2. So my y value will be 5 halves times square root of 2 over 2. And my x value will be 5 halves times negative square root of 2 over 2. And I know I have them backwards, but my final component form for vector v will be the x value comes first. So it's negative because positive times a negative is a negative. 5 times square root of 2 is 5 square root of 2. 2 times 2 is 4. And then we'll have something similar, except I have positive types of positive is going to give me a positive. And we will put that little bracket and a box around everything. And we will say we are finished. And that is all I've got for today, folks. So, the Star Wars fun fact of the day. The world capital city of Coruscant never actually appeared in the original Star Wars trilogy. The name was coined by the author Timothy Zahn in his expanded universe book, Heir to the Empire. George Lucas liked it so much that he made it canon for the prequel trilogy. So maybe if you write a Star Wars book that's good enough, Disney will make your ideas canon as well. All right there, folks. That's all I got for today. You have a great day. Goodbye.